morning, Sanjay.
Morning. So did you get the assignment sheet?
Yes, yeah, I already uploaded it in the this assignments folder. So I think it should be available to everyone now. Deku from ISER was supposed to join. I don't see him here. Okay, maybe you can just present the screen.
Okay. Yeah, guys, yeah,
so see whether this is coming in the presenter view or. Okay, I think this appears good now.
Oh. Is it very full view?
Yeah, now it came back to the presenter view. Actually, it was okay.
Was earlier was good.
Okay. Yeah. This is good. This is good. Okay. Now I think it is already 10 o'clock.
Right.
So I hope you don't have to wait. Riku is here now. So Riku. Okay.
Oh, hello, Sunil. Yeah.
Yeah. Good.
So we're good, right? Yeah.
Yeah.
So thank you, Mr. Majumdar. Yeah, thanks, Sunil. Yeah. So it's a pleasure. I'm Raghu from ISU Tirupati. Yeah. So I shall be, your host for today's session. Yeah. Thank you very much, sir, for giving this wonderful series of lectures, and we look forward to some more very interesting aspects of quantum optics today. Yeah. So with this, without further ado, I would love to hand over the virtual podium to you. And for the participants, if you have any questions, if you also type them in the chat box, I'll just pick them up and then I shall, put it out to Professor Majumdar's for his reference, so that the questions may be answered. Yeah. So over to you, Professor Majumdar.
Yeah. Maybe. Yeah, you are audible. Maybe, Riku, I think during the lectures, Abhik will be passing the questions. At the end of the lecture, there will be some questions which probably you can read up and then take care of. So this can end with that vote of thanks session. I think that was how it was all through these lectures. So this is the 7th lecture, right?
This is 7th lecture, right?
This is the 7th lecture. Yeah, we have 3 more to go. Yeah, and 2 tutorial sessions. 1 is tomorrow, I guess.
So let me start.
Yeah. Please go.
So good morning, everyone. So it's a heartiest welcome for the 7th lecture. Before let me start the lecture, I just remind you. So there will be tutorial sessions tomorrow afternoon. So one set of assignment already circulated to you through the proper channel. I think the Google Sheet which you access. So please work them out and be prepared before coming for the tutorial so that it will be useful for you. Okay, so you can ask questions, and if you have any doubts, because I get some mails from you which I couldn't reply maybe some of the times through the email. But if you can raise these points into tutorial sections, okay, it will be useful in the sense that it can be interactive way to interact with you. Okay, so I think please ask the question in your tutorial some of the things which already have been taught. Okay, if you have any doubt on them. So let me start by recalling what we have discussed in the last class. So you remember that if you are able to see the cursor on the screen properly, that we have discussed that squeeze state of light. Okay, we have talked about how the squeeze state of light can be generated in the lab. Okay, and we have talked about that actually what it means, squeezing of light. So as we have said that mathematical font, okay, so you can have an operator like SR, which is expressed in terms of the second power of creation and annihilation operator. And if you operate in either of the quadrature, position and momentum quadrature, what you see that you will get the squeezing of the either of the quadrature depending upon the value of the R. Okay, R is a parameter which actually says that how much is squeezing. So you see that if value of the R is positive, okay, and if it is very large, what you see that Q quadrature. That means that your span of the position, okay, for a particle, so movement of the particle in the physical space, okay, that will be squeezed. At the expense of that, you have to bother that you should not bother about the momentum precision, okay. In the case of the when you are talking about the squeezing of the position detection, you don't bother about the momentum. At the same time, if you don't bother, you should not bother about the energy of the systems. Okay. So if you say that R is less than 0, what you see that this expression tells that this is the amplification of the position span. Okay, whereas you are squeezing the momentum. So if you are really bothered about the energy, okay, or momentum of the systems, okay, so you should actually look at. And you know that each photon carries actually uniform energy and momentum. Okay, so that's important here. So if you want to look deeper instead of the position and momentum quadrature, if you want to go for the creation annihilation operator, this operation is like this one. Okay, so that your A will be looks like that A cos hyperbolic function will come and minus A delta sine hyperbolic. So you just have to work it out and find it out. So when we talk about the squeezing operator on vacuum, that is 0 photon state. So here, what you see that it will be called as a squeezed vacuum. Okay, so that we are denoting by R. Okay, so that when we say that this just R, okay, that means that is squeezed vacuum. You are squeezing the vacuum. And depending upon R, whether you are squeezing the position or momentum for it, it will be defined. Now, if we have that, if you want to try to find out how many photons are there in the squeezed vacuum, which actually there's no photon. Okay. So you can just calculate it using the number operator. Where number operator you can expand by A dagger and A. Okay. And you calculate it, and what you will find out it is sine hyperbolic R square. What does it mean? Means is that this diagram which is showing, okay, you see that as R goes to R increasing, okay, what you see that the sine hyperbolic R square actually is diverging, it's going up and up. So increasing like anything. So that means that when you squeeze the vacuum, you will get the more and more number of photons. And depending upon the squeezing, your number of photons also increases. Then, if you want to say that if I squeeze it to the infinity, that means if R goes to infinity, so it is extremely squeezed, okay, then in that case, what you will get, you will not, as you understand, you will not get any dispersion in the position. You'll get accurate position measurement, like you will find out in the central part of the position axis. Okay, but in that time, what would happen? Your momentum or energy, okay, uncertainties will be very large. Okay, so you have to just bother about the amplification of this other quadrature. So here we are considering r greater than 0. So what would happen that this amplification will happen in the momentum quadrature, and we realize this in terms of energy. So when you don't bother about energy or momentum of this particle, you are well advised, okay, to go for the position precision experiment, like LIGO experiment, where actually that when you do the gravitational wave detection, you just want to have that how much actually movement happened to the atom, so how much actually displacement happened. Okay, that amount, if you want to find out very precisely, okay, you should have the squeeze right. Okay, don't bother about the energy of the photon which actually impinging on the atom. So, and so we have checked that rather what is the energy corresponding to the vacuum, which is squeezed. Then what we saw that as we discussed that we are squeezing either of the quadrature, either position or momentum. Similarly, we can understand this in terms of the amplitude and phase. Okay, so that is also possible. But here, what we are just talking about the electric field of operator. Okay, if you just have the variance of the electric field operator with respect to that squeeze state, okay, what you will get this kind of expression where without the squeezing, okay, you would have that just n square, that amplitude square of the electric field. Okay, so once we have the extra terms, these extra terms, what is the meaning of that? What you will look at carefully that if you can just separate out the electric field in terms of the position and momentum quadrature, and if you operate that the squeeze state on them, so your variance looks like these two terms. Okay, so this is for position quadrature, this is for the momentum quadrature. Now, if I just want to say that let's r equal to 1/8, which is greater than 0, and let's say that we are having omega equal to 1. Okay. So what we can have that, we can just say that over the time how this squeezing evolves. Okay. So at time equal to 0, what you see that blue line says that what will be the momentum dispersion, okay, of the electric field. And you see that momentum dispersion at t equal to 0 when omega equal to 1, okay. So what you see that if r greater than 0 is higher, at the same time what we got it position. We got the position dispersion is very low. Okay. If you evolve the systems over time, what would see that these squeezing of the position and momentum quadrature of the electric field sharpens. Okay. So what would happen after time, let's say pi/2, keeping the omega equal to 1, that is the unit of the omega. Okay, what you will see that system evolves and you got the squeezing in the momentum space, whether the position space, okay, it is amplified. Okay, so what you will see that over time, as I showed in the last class, that if you want to plot, okay, the uncertainty sphere or circle which was there for the quantum state, okay, or vacuum state, okay, in the position and momentum quadrature, okay, and that will be squeezed in a particular direction, either momentum or position, and over time, what you will see that will be just shuffling, and you will have a rotation of this structure. So I believe you have understood that, as I explained also in that kind of experiment where squeezed lights are used. Okay, you have to wait till the time the pi comes, so that you will get the position squeeziness again comes. Okay. So if you started at t equal to 0, again you have to wait till the time t equal to pi, so that you will get the squeeze state back in the position again. Okay. So that's actually you have to bear with it. Then what we try to generalize, okay, we've seen in the last class that this squeezed operator, okay, depending upon that, your incoming or palm flight, okay, giving some kind of phase, so that you will get extra degrees of freedom using the phase terms of phi, where this is your incoming light and this is the amplitude r by 2. So if you just consider that and you go back and work it out for your Hamiltonian, interaction Hamiltonian, what you will find out that your squeezing operator will be depending upon not only R, also it will be dependent on phi, and you will get the expression like this. Okay, where that you will have the extra phase vector comes with the both creation and annihilation operator. In that case, what would happen? You just work it out. Okay. So I'll suggest to give it an assignment. Okay. So if you just calculate, you will get the extra phase compared to earlier one in this A dagger terms here. Similarly, if you calculate for A dagger, also you will get the transformation relation. There is a phase terms coming there. So what you can just look at in that case, okay, if you work out the generalized squeezed operator, okay, what will, if you just work out the position and momentum variance, okay, so what would happen that you will get extra terms compared to the earlier one here, that are cos phi and sin phi terms. Cos phi terms are coming for both. Okay. So these extra terms are coming because you have incorporated the phase terms in the incoming pump light. Okay. Now, so it is in your hand that whether how much phase you want to include it. And you see that you can include phi equal to 0, phi equal to any values, okay, pi equal to 2 pi, whatever it is. So if you phi equal to 0, that means that you are still in the no phase shift region. But if you put the phi equal to pi, so what would happen that you will have this cos of pi to be minus 1, okay, and what you will get the change in the sign. So in that case, what would happen when phi equal to pi, okay, that squeezing which was done actually in the phi equal to 0 in the position quadrature, it will be shuffled to the momentum quadrature. So what would happen that if you just see that in this case of the when phi equal to 0, what you had that your squeezing was there in the position quadrature, keeping the r greater than 0. Okay, so that is squeeze this because of this extra factor with the amplification of the momentum one. Now, what you will see that the momentum quadrature, actually this is amplified, and here you see that position quadrature is actually squeezed. When pi equal to phi equal to pi, then it will be in opposite, that you will get the squeezing in the momentum quadrature, whereas the amplification will be there in the position quadrature. So what you can have, apart from what we said, that if you keep the system over time, that position and momentum quadrature shuffles, also you can have a control from outside, okay, to choose which one you want to start with. You can, by choosing extra, if you give extra phase to the pump light, you would be able to control that whether you want to start by choosing the squeezing the position quadrature or squeezing the momentum quadrature. So I believe you understood both the control mechanisms. One is over time, if you keep it. Another is that external control, which is in your hand. Okay. So earlier one was not in your hand. That is by default, it will just evolve over time. And now this is in your hand, that how much phase shift you want to incorporate in the systems. Okay. Depending upon that, whether you will get momentum squeezing or position squeezing. Okay. So that's, I think you should keep in mind. So once you have these ideas, okay, now let's go back. So this was the whatever discussion or the vacuum state. Now we will be more interested when there is some number of photons are there. That means quasi-classical like laser light kind of things, which is also considered as a classical means the coherent light. Okay, so that whether we can squeeze the coherent state, and if we squeeze them, what would be the property of that squeezed coherent state? Okay, so as you remember that in the position and momentum quadrature, okay, when we want to have uncertainty, okay, from the uncertainty of the position momentum, we was obtained that it was a circle with a radius of square root of h cross by 2, okay, for the vacuum. And when we want to have the coherent light, okay, we have to, depending upon the value of the states which we want to look for, that if it is alpha state, keeping the any complex value alpha, okay, you can apply the displacement operator, and there also that you will get the any point in the space of P and Q, okay, having the alpha is the distance between these 2 points and from the this point from the center, okay, what you will find that you will see that you get a similar kind of dispersion circle at the coherent state also. Now, thing is that as we have explained that we are able to squeeze the vacuum state, okay, either momentum or position, okay. Similarly, if we now apply the displacement first and squeeze the systems, or if you can squeeze the vacuum and displace, okay. So that is the 2 options are there. So either you squeeze the vacuum level itself state and displace it so that you will get the coherent state which will be squeezed, or in the same time what you can do that you can do the transformation from the vacuum to the coherent state, the quasi-classical kind of lights, and then squeeze it. Okay, both of the cases you will get similar result. Okay, and you can do the I can give an assignment that you can use the transformation relation and try to prove that whatever the output will be there in both the cases will be same. Okay. So whether you apply S first, then D alpha, or whether you apply D alpha, then SR, okay, it will be giving you same. So we are denoting this squeezed coherent state as alpha comma R. So what you see that we'll get that squeezedness in the either here I have shown that in the moment position sector, okay, that we are giving an example as a picture, okay, squeezedness in the momentum sector, okay, momentum quadrature, okay, in the coherent state. So I can just assign you that if you want to look at how this annihilation operator, okay, behaves under this squeezed coherent state, what you will find that you will get back the alpha value. Okay. So and if you do it for the S square, okay, you will get alpha square, your I phi sine alpha R cos hyperbole R. This is giving a hint that so that if you want to find out the population of the squeezed coherent state, okay, so that means you are trying to find out what is the expectation value of the number operator, okay, with respect to that squeezed coherent state. Then you just replace number operator by a dagger a and do these operations, okay, and what you will find that unlike that for coherent state, your population is alpha square, okay, you will get extra terms as you got it in the vacuum where the population was 0, you got that after squeezing, you got sine hyperbolic square. Here also you will get the extra terms, the sine hyperbolic square R, okay, plus that what was there in the coherent state, the number of photons, okay. So as you saw that sine hyperbolic square R actually shoots up with the increasing value of R, okay. So what you will get that population also of this coherent state shoots up, even if you take the low value of alpha, which actually dictates, okay, how many number of photons are available in the coherent state. So once you squeeze that, okay, you will get the very large number of photons in the systems. Okay, so if you just squeeze the laser light, okay, you will be able to get many multiples of the number of photons in the system, in the light. So what you can just also look at it, this is as a byproduct, okay. If you want to just see that what happened to the momentum position quadrature, if you operate the squeezed quant state in the momentum quadrature, and you just apply these identities, okay, so that here you just replace alpha r by the s dagger d dagger. Similarly, in the Kate side, d is, okay, and then you work it out for first for the displacement on the position operator. Okay, then you apply that transformation with respect to the squeezing operator. Then what you will ultimately get, you will get the similar kind of expression which you got in displacement cases, that your system is displaced by the amount in the position quadrature, the direction of the position axis, okay, square of 2 real value of alpha. But what would happen that uncertainty when you calculate, what you will see that these will be squeezed, okay. So though it will be displaced in the along the position quadrature, position axis, okay, but the kind of uncertainty which you will get, that will be squeezed. Similarly, you will try to see that what would happen to the momentum axis or momentum quadrature, okay. So here it will be in imaginary direction, imaginary values. Okay. The amount will be coming from the imaginary values of alpha. Now, next, what you can do. So there is some application I am just want to show that now you see that if you apply that quant operator, alienation operator on the vacuum or on the zero photon state, what you will get that zero value. Now, if we just operate that squeezing operator from left and use the identity that S dagger is unitary, means that S dagger is equal to 1. So what you will find that you will find the transformation of A, alienation operator with respect to squeezing operator, okay, and the right hand side you will get the squeeze state of the vacuum. So ultimately what you will get that this will be transformation of S dagger, sorry, there will be dagger here, so S dagger actually, okay. So is dagger, no, I'm right, okay. Is dagger and this is SR, fine. This is exactly perfect, okay. So that what you will see that this transformation will give you some cos hyperbolic A plus sine I phi, if you have a generalized exponent of I phi sine hyperbolic R, okay, on this, that is a factor for the A dagger operator. Okay. And that is operating on the squeezed vacuum, okay, and it will give you 0. So ultimately what you will got, that you will got a operator operating on the squeezed vacuum will give 0. So that means what you can say that squeezed vacuum, you will be able to get it from this operator, okay, as an eigenstate of this one. So if you can somehow generate this operator, okay, one of the eigenstate of this will be the squeezed vacuum, but it will have the eigenvalue 0. So if we extend it for the quant state, okay, so when you have a squeezed quant, what will happen that similar thing will be there, but what would happen that this squeezed quant state will be eigenstate of this kind of operator with the eigenvalue, but there it will not be 0, that is, but it will give some kind of value depending upon how many photons were there in the quant state. So if you have a alpha square number of photon, so that alpha factor will come with the cos hyperbolic and sine hyperbolic terms, and you will get the eigenvalues. Okay. So here what would happen that you can see that how the squeezed quant states are eigenstates of the particular kind of a operator, which is a mixture of the creation and annihilation operator. So this is, you can just work it out and find it out. Okay. Now, once we have it, okay, so what we have looked at, we have mostly looked at the position and momentum quadrature, how the squeezing is going on. Now, if I would like to look at it, that the population and phase distribution, the same one, we want to just convert it. And what we'll see that if for a quant state, okay, where actually if you have a number of states, okay, the mean values of this one, let's say that let's say instead of n, this alpha, you can consider value of alpha is such that mean value of this one is 8.4. That means this is the alpha square term, okay. And because of the coherence, okay, what we expect that variance also should be same as, almost same as this one. And in that case, if you see that how the particular value of n, okay, is populated in that coherent state, okay. So we want to plot the probability. So this will be probability in nth state populated in the particular alpha state, okay. What you will see that there is kind of Poissonian distribution, okay, which we expected earlier and we have discussed earlier. So here there's x-axis photon number, y-axis is the probability. Now once we squeeze the amplitude, what would happen that you expect that the variance will be squeezed, okay. So that means variance will be smaller than this one, the mean value of this distribution, okay, number distribution, okay. So here number distribution, let's say this is an example 8.9, and so it is actually what you get variance is 4.9. So what you'll see that the photon number distribution is squeezed compared to what you saw it in the coherent light. Whereas phase squeeze cases, okay, so where actually you are not bothered about the amplitude squeezing, okay. So and what would happen, the variance of the alpha. So instead of n, you can think of alpha, okay, which will be much larger than the mean value of alpha, okay. So that actually will be giving you some kind of broad spectrum of the photon distribution over the number space, okay. And that will say that this is actually can be the squeezing of the phase space in terms of the amplification in the number space, okay. So that's a picture what you will see that in the terms of the distribution of the population. If you look at the distributions in the phase sector, okay, what would happen, what actually we understand if we say that there is some kind of a Gaussian kind of distribution which we get for coherent light for very large value of alpha, as we know that. So what would happen that if you have a x-axis phase, in case of phase squeeze, okay, that spread of the phase profile which we saw it for coherent light, okay, that will be squeezed. And but what would happen that this will be shooting up because that is a amplification will be done, okay. Whereas the amplitude squeeze cases, okay, you will have the spread in the phase directions, but amplitude will be compared to the coherent state will be smaller. So that's the kind of distribution, okay, you will see that in the case of squeeze state. So far now we are talking about a lot of theories. Now let us see that whether we can do some kind of, or you can understand some experiments, okay. So for that, one of the beautiful quantity which actually purely in the quantum nature is called short noise. What is the short noise? Let me explain it and then we'll go. So consider that when a coherent light is coming to the beam splitter, okay. So coherent light, I am saying that it is alpha. Now once that coherent light is coming to the 50-50 beam splitter, say, okay, so which is lossless, and what we learned so far that half of the lights will go to the third detector, half of the light will go to the fourth detector. So because it is 50-50, okay. But this depends upon that whether that is a laser light with a large intensity large, a strong laser light. Okay, so that means alpha value is large. Now, if I say that instead of the laser light, which is having a large alpha value, where the number of photons are 10 to the 5 or 10 to the 6, instead of that, if I have 1,000 number of photons are impinging on the beam splitter, which is 50-50, what would happen that what you see that in the experiment, you will see that in the DT detector, okay, the third detector, you will get around 550, whereas in the D4 detector, you will get 450. That is experimental fact. Okay, you will get this kind of. So what will happen that in terms of percentage, okay, which was 50-50 earlier because you have a large number of photons, okay, which is actually now it will disperse from that 50-50 to the 55-45. So if you just go down and use the less number of photons, like 100 photons, okay, similar kind of a variation from the mean value, okay. So what will give that percentage of deviation from the 50-50 is large, okay. So you will get now 60-40. So here from the mean value, we saw that 50 photons has gone extra in the third detector, 50 photon was less in the fourth detector. Similarly, if I say that 10 photon was extra in the third detector, 10 photon was less in the fourth detector. So the percentage wise it is increasing. So if you have 10, it is that. So what would happen? Though we don't realize this kind of dispersion from the mean values, where we have a large number of photons are there. But when you talk about that small number of photons, where actually we are interested, we see the quantum phenomena there. Okay, so we see that in the statistics, okay, when you do the detections, okay, there are some kind of a large dispersion. Comparatively dispersion in the photons. Okay, so it's the statistics. So these actually will be there in the statistics when we will have the incoming photon. As you remember that here what we are having that a number of photons are impinging on the beam splitter. So how the number of photons coming one after another. Okay, so that actually giving you the statistics. So if your number of photons are coming, so a lot of number of photons coming together, a few number of photons coming together, or one photon is coming at a time. Okay, so depending upon the number of incoming photons, that is the statistics of the incoming light, okay, actually will give this kind of a variations. Okay, so what you see over the time that for number of trials, if you just use it, okay, so what would happen? Here you see that when you have the lower and lower the number of input photons, okay, your fluctuation of the number of photons in the detector is becoming large, okay, the percentage wise, okay. So that's actually can be understood as a short noise, okay. So that is there inside that is intrinsic to the system, okay, and that will be able to obtain in the detector, okay. So this is some kind of things which is statistical, which is random, okay. So and this is actually the phenomena of quantum optics, okay. So what you see that the quantum fluctuation in the detection of the number of photons, okay. And these kind of a noise, okay, which actually is there inside system are known as short noise, okay. So this is very important only when your finite number of photons are available in the wave packet. If you have a large number of photons like coherent light, laser lights, okay, which is having 10 to the power 5 or 10 to the power 6 number of photons, okay, this is not a important phenomena there. But if you have a very low number of photons, okay, like 1, 2, 10 kind of number of photons which are coming and hitting the beam splitter, they are actually, this is really significant. So we need to look at it. So short noise is a phenomenon which is a very, very fundamental to the system itself, that light itself. So if we just want to see that short noise of a quantized field, okay, so this is, as I said, this is statistical. This is also that this noise is intrinsic to the property, okay, and it's random. So these also can have a resemblance, okay, with the thermal noise, okay, which actually we get or observe them, okay, when the temperature is large. So in the system, if we can cool down the system very low temperature, we'll have a control on the thermal noise. But the short noise will be still there. We have to go with that. Okay. So now, so important is that by cooling the systems, we are not able to get rid of the short noise. Okay. So we should look at how to reduce the short noise. Okay. So let's see that our idea of squeezing the light, whether it helps or not. Okay. So if we consider that for a large value of alpha, where actually number of photons of the quantum states, okay, is large, okay, and that is called a quasi-classical states also. So we saw that that Poisson distributions, which was for the quantum state, for large value of alpha, it will be like a normal distribution or Gaussian distribution, where mean equal to variance. So this is the known things which we have already discussed many times. Okay, let's recall it. So standard deviation, okay, for this kind of light, okay, which also called the short noise, okay, which we have learned so far, okay, is square root of the mean value of the photon. So for quantum light, okay, short noise is nothing but square root of the mean value of the photon. Now, thing is that here what would happen that if you have the signal to noise ratio, okay, so noise is in the denominator, signal is in the numerator. So as you know that for quantum light, that mean value of the photon is alpha square and standard deviation is alpha. So ultimately, depending upon value of alpha, which actually is large for laser light, okay, so we don't realize this kind of a noise, as we have explained on last slides also. Okay. So what we should look at, we should look at the systems, or we should look at the light, okay, where actually your standard deviation, the fluctuations are less than that normal distribution things, okay. That means Poissonian distribution. So if you have that standard deviation is less than the square root of mean value of n, okay. So where actually you will be able to look at some systems or light which is sub-Poissonian in the nature. So we'll have a sub-Poissonian distribution. So, and that can be observed, okay, if you have a very low number of photons are there. So lower values of the alpha, very low value of you will be able to see. So there actually you will get that short noise, very dominating figure, okay, and significant for your experiment. Okay. So here, so we have, I believe you have understood what is short noise. Now what I just want to show it that how to squeeze this short noise. Okay, so as you understood that short noise is nothing to the but the this what you actually can play with the amplitude of the electromagnetic field. So as we have understood so far that we can squeeze the position quadrature, we can squeeze the momentum quadrature. Similarly, we also saw that we can squeeze, okay, if you like, where actually you can squeeze the amplitude, okay, uncertainties or fluctuations, okay, at the expense of the phase fluctuations. Like the example is given here. This is the case where you have quantum uncertainties. Okay, quantum state is situated, and uncertainty of the quantum state is that circular disc. Okay, having the amplitude, okay, square root of h cross by 2, or radius is h cross by 2. Okay, and what would happen if you squeeze the amplitude in the radial direction? Okay, what would happen that you are getting the some kind of oblate shape spread of the uncertainties, okay, which is actually squeezed in the radial direction but elongated in the azimuthal directions. Okay, so the azimuthal direction is your phase, which we are actually being amplified due to the squeezing of the amplitude. Okay, so in the case of quantum light, you will see this picture. In of amplitude squeezed quantum light, you will see this kind of pictures. Okay, so here what happened that if you want to squeeze this, okay, what you are doing it, you are making the uncertainties in the number distribution. Okay, so that is your standard deviation of the number operator. Okay, or number state, number of photons in the state. Okay, standard deviation of the distribution, I should say. Okay, that is less than compared to what you got in Purcinian cases. Okay, that your this standard deviation is square root of mean value of n for the Purcinian cases, and what we are getting less than that, and that actually says that we are in the domain of sub-Purcinian statistics. That means we will be able to see this kind of statistics only when I will see that show the example where actually we can see that when this sub-Purcinian statistics is dominating, and it will be possible to show that when you have number of photons are very low. Okay. So what would happen that if you want to see that how much the standard deviation in the phase, okay, that is an amplitude, and a phase will be now what you can show that is if you just add the vacuum state or point state, as you know that phase and amplitude standard deviation, okay, that goes by equal to h cross by 2 minimum uncertain state. So that phase variation, okay, a phase fluctuation we can write is h cross by 2 times, so in the denominator that is delta n. So that is the fluctuation of the density, okay, or intensity, what I say, of the photons, okay, not density, intensity of the photons, okay. So what you see that if you consider the large number of photon in the your light, okay, these values become very, very small. So what would happen that you can squeeze this phase, okay, for a laser light kind of things where actually your number of photons are very large. So that means these states will be more coherent in the case of large number of photons availability. Whereas okay, that if you go for low number of photons, okay, your these values, that fluctuation in the phase will be large. Okay, so and that means that if you are just considering that a system where fluctuation of the phase is large, you'll be able to squeeze the amplitude of the light. So
excuse me.
sorry, yeah.
There's a question in the chat box.
Right.
It reads, what is short noise limited?
Yeah. So let me go back. Yeah. So what is the question?
So what is short noise limited?
Short noise limited.
Yeah, that's the question.
I didn't get the question, but I think what is asking that how to limit the short noise. Okay. If I just reframe the questions, okay, that means that the question will be that whether we can control the short noise. Okay. So that is the question which I am going to address it here. Okay. So as you see that short noise, which is very intrinsic to the statistical nature of the light, okay, and which you can't control by cooling down the systems, unlike that thermal noise, okay, which is also same statistical and random in nature, okay. Here, what would happen? Short noise, okay, if you can squeeze your original beam, apply it, okay, what you will see that you will be able to squeeze the short noise also. So that is the point which I am just going to address it here. So we can make that short noise squeezed, or the dispersion in the short noise is smaller, okay, as we use that squeezed light. I think that is the answer to a question, if the question is framed it like that.
Okay.
Okay. So what we saw that I hope I am not going too fast. Okay. So we want to just you understood that that we want to squeeze the amplitude here. Okay. At the expense of the phase. phase we don't bother. Okay, so here actually your idea is to that squeezing a short noise, okay, with the help of the squeezing of the amplitude. Now, to understand how we can get it through our experiment, okay, we just again go back to our understanding of the beam splitter homodyne kind of detection. Homodyne because your local oscillator and signal was having the same frequency or same wavelength of the light. That's why I call it homodyne. If they are having the different frequency or different wavelength, okay, they will be called heterodyne. Okay. So what would happen if you remember that when that signals is coming along with the local oscillator, which is in the orthogonal port, and coming impinging on the beam splitter, and you are detecting in the third and fourth detector, okay, and then what you do, you just wire these detectors and do the calculation, addition and subtraction of the photocurrent which is obtained from the photodiodes of the third and fourth. Okay, so what you will get that these kind of things that when you just add this, okay, current, okay, we'll get total number of photons. I think you remember that. Just recollect it that if you add the current from the third diode and fourth diode, if you just add them up, this current will get the total number of photons. Whereas if you subtract, what you will see that you are getting the mixing of A1 and A2, which was coming through the input channels, okay, as a local oscillator and signals, okay. And what we showed in the next slide, okay, that after adding this one, if you do that, okay, you show that if you have that local oscillator which is coming from the second input port, okay, as a kind of you can write as a coherent light, okay, so that's quasi-classical kind of a light. So you can write it as a beta exponential I omega t, okay, beta is complex number which is having a phase. That extra phase you can add with the beta, which is coming with a local oscillator, and we know that how this extra phase can be incorporated in the light using the phase shifter, okay. And so what you will ultimately get that you remember this kind of a table where we have shown that extra phase which is there in the local oscillator, controlling that psi values, okay, what we will get that depending upon psi value with the extra pi by 2 which is coming from the just coming the expressions, okay, what is the total theta, what we got it, that theta equal to 0, that means the psi equal to minus pi by 2 when we have this phase, okay, we get that the amplitude of the signals. So we got the A plus A dagger by 2. That is nothing but the amplitude of the signals. And when we subtract, when we got that I minus and putting that theta equal to pi by 2, corresponding psi equal to 0. Okay. So in that cases, when local oscillator will not have any phase shift, okay, then what would come? You will get the phase of the signals. Now, what we will be interested when there will be actually amplitude can be measured, okay, through this homodyne kind of this experiment, keeping that psi equal to minus pi by 2. So that if psi equal to minus pi by 2, theta is 0, we will get signals, and we are interested to that, okay. So these idea which we have discussed so in the last I think classes, okay, so that you will be applying here again, okay. So just recall that what we got that I minus by subtracting the current, and which is nothing but what the way we wrote, it is that local oscillator amplitude, which is a coherent light, strong coherent light, okay. And we got some quantity which is proportional to the phase of the local oscillator, that phase shift what was incorporated in the local oscillator theta, okay, that depending on that will get terms. So that actually with the signal inputs, okay, so we'll get this quantity or this operator x of theta. So that these x, which actually, as we have seen that depending upon theta equal to 0, okay, we get that a plus a dagger, that will give you the amplitude of the signal, okay, that if you remember the picture, this will give the amplitude of a signal. Again, I'm just showing that that this signal, okay. So that actually we are interested here, and that we can obtain easily, okay, in the case of variance also. So if you just want to calculate the variance obtained in the subtracted current, okay, so you just will see that that will be nothing but a variance in that particular kind of phase quadrature, what we can say that kind of operator. Okay, so that variance will be actually coming here, as we know that for point light beta is fixed. Okay, we are just having the mean value here. Okay, mean value of the point light, which is coming as a local oscillator. Okay. Now, just if we just want to find out, if you want to make it that these subtracted current variance, okay, is lesser than the mean value of the point light, which will tell me that this is a sub-Poissonian kind of a nature. Okay, this has a sub-Poissonian kind of nature. For that, what we have to do that, if you see the expression, we have to make that the variance of the quiz quadrature has to be less than 1/4. So if we can set this one, this is very important. If we can set this one, okay, is less than 1/4, okay, then what we'll find that we'll be able to go in the region where actually that short noise, or what we call the variance, okay, in the current, okay, the subtracted current, which will be less than the mean value and showing you sub-Poissonian kind of a signature. So our target is that somehow we have to make this is less than 1/4. Then we'll be able to say that the kind of the signal which we had, that was a sub-Poissonian. So that's actually ultimate goal for it. So please remember this statement. So and this is, as I said, this is highly possible, okay, by changing the local oscillator phase. So what we are talking about, so amplitude squeezing, okay, by this technique, okay, where we want to go that standard deviation or variance should be less than that, whatever same is for the Poissonian distribution. So I believe that you have understood that what is short noise for the point light. So that is nothing but the standard deviation, okay, and which we can get it by square root of the mean value. Okay, that is short noise for the point light. Now, if you want to squeeze this short noise, what would you have to go? You have to go to the sub-Poissonian distribution. Okay, if you go to the sub-Poissonian distribution, automatically, okay, as the number of photons is less, okay, that amplitude will be squeezed, okay, and what will get your signal, okay, the short noise also, will be squeezed, okay, or due to that your signal is being squeezed here. So that is the one. That is the only way we can just squeezing the short noise, by choosing the sub-Poissonian distributed light. Okay. So let's go back to the homodynamic detection technique once again. So I just want to just modify a little bit. Okay. So because we have to find out in the last statement, you see that what we have to find out, we have to find a signal which will be less than the short noise from the point light. Okay. So if you have point light short noise, okay, that is going to square root of mean value of n, and we want to make that is the reference level, okay, and we want to go below that, okay, to get the sub-Poissonian distribution. Okay. So what we do that, we just having only one input port, not one port, and as a result that other input port is available, but there is nothing is that means that one. So what would happen that if you have only one input port, you have the two detector 1 and detector 2, the photodiodes, okay, and we have wired them up, and the current what you will be getting from both the detector, either we add them up or subtract. So that addition will give that, if you have that, if you have vacuum here as the input port, okay, what would happen? Addition will give you the whatever fluctuation inside the vacuum, okay, that will be added up. The total fluctuation will give from the if you add the current, isn't it? So if your input is vacuum here again, okay, that will give you that will give you the total fluctuation as addition. But if you have a subtraction of this current, which I'm saying the minus as output, okay, in this kind of a balanced homodyne kind of system. So here both of them are vacuum. Okay. So what we will get that, as you see that we get that x of theta, and there is no phase incorporated in the vacuum. Okay, with the theta equal to 0, and these x, okay, vacuum that varies. Okay, this actually, because there is no signal, says that we can set it as a 0. So we can set that the mean values of this x is 0. So then what about the variance will be there? Variance will be giving you, okay, the in that -1, okay, when inputs are the vacuum, okay, it will be that your short noise. Okay. So the output of will be the short noise level of this one, okay, in terms of variance. Okay. So and this discussion you will be able to see in the Mark Fox books, okay, of introduction quantum physics. So once we get the vacuum input and said that what is the short noise, okay, in case of the vacuum, what would happen that you can say that is the vacuum level short noise, and that is here it will be almost 0. But now if you have that your input having some kind of a point light or laser light, okay, you will be able to see from the subtracted output, okay, again that you will see that what will be the x theta for theta equal to 0, okay, and that will give you the variance of that will give the short noise for that coherent light as which is coming as the input. So in this case, what you see that we blocked that this other port. Okay, so there is nothing is coming. We are making it such that nothing is coming. Even vacuum also not being able to observe here. Okay, so that what we saw that only one input channel is open, and there actually we kept initially vacuum, then we gave the your coherent light that which actually we want to use as a local oscillator in later case. Okay. So now. So that is the experiment which we have done. Okay. So here, okay, what we see that now look at it in different way. So here is a signal now. So and what was discussed here is a local oscillator. Okay, in the last slide that is coming in from the bottom. So now we are opening both of them. Okay. So both the input channels are open. Okay. What was opened earlier as a local oscillator, now it's still open. Okay, and we are naming it as a B associated with the B operator, and signal we are associating with the A operator. So now if we see it, okay, what would happen? Just a few minutes, okay, please. So what you see that the A, now if I use some kind of a sub-Gaussian signal, okay, let's say some which is actually I want to test it, but I'm just saying it if it is a sub-Gaussian if it has in sub-Gaussian statistics, what would happen that because A is very B is very strong, okay, that local oscillator is very strong, okay, what you will have that okay, you could write this C, whatever light is detected in that detected D, okay, that is nothing but that associated with the C operator, and C we can write that transmittance of the A and plus the reflected by the B. And the I extra phase coming because of the reflections. Okay, so that this is nothing but your reflection coefficients. Okay, so ultimately what you will get the TA plus IRB. Okay, now since what I say that I am just obtaining that whatever intensity is coming in the detector. Okay, and that is nothing but we can write it C delta C. And now if I just write that C, whatever we got it here in terms of A and B, and if you just derive it, okay, C delta C, what you will see that you will get a term which is nothing but T square A dagger A, and this A dagger A is nothing but your intensity of the light which is coming as a signal, And the signal, what I'm saying, that weak signal we are using because it is sub-Poissonian. Okay, so that is very weak, that very small terms. What about that? This one, that this is nothing but your reflection coefficient square and times with b dagger b, and this being the strong the local oscillator. So intensity of that local oscillator is very high. So the term which will be this will be dominating here. Okay. Now what would happen that you will get additional terms because of mixing of these two two lights. Okay. So what would happen that, as we have seen earlier also, you will get a b dagger minus b dagger a dagger b. Okay, with the coefficient of this one. Now, if we just neglect this first term, which is actually very small compared to the other terms, as that terms associated with the b or b dagger, okay, then what will happen that we'll have first term is this one, that second term as the first term, and these terms, whatever is the third in the parentheses, okay, that one which we can write is that whatever we saw it as a phase quadrature, okay, which is depending upon both signal and the phase of the local oscillator. Okay, so that this x is dependent on both the signal creation or annihilation operator and the phase of the local oscillator. So depending upon the phase of the local oscillator, you can modulate this. Okay, so what we can see that, so this one, the first terms, okay, this is the intensity of the local oscillator times the reflection coefficient square. So that if I know that it is a 50-50 unit speed, also this will be, I know that what is this half, nothing but half. So, and I know that what will be the intensity of the coherent light, which is coming as a local oscillator. So you can subtract that, whatever you got it in the signal which you got in detector. So what will be left to it, will left to the second term. And that second term, if we just divide with the beta, which I already know, okay, as a intensity square root of this intensity, okay, and if I know that t is half, okay, so what I'll be able to get, that I'll be able to find out what is x theta. Okay, so what actually x theta is nothing but, as you have seen, that we would be able to write it in terms of the signals creation and annihilation operator and the phase of the local oscillator. Yeah, so as I have explained that we will get a first and second term. Now what would happen that, so from this detected signal at detected t, we could plot this x theta versus theta. Okay, so if I just want to just let me go to this. So yeah, so what we got it, we got that x theta variance, okay, with respect to the theta. So, and what we see here, that once we have that low signal, okay, that intensity of the signal is low, then if we could see that these you are able to get a delta of x theta, or that is the variance of x theta is going less than 1/4, okay, for a particular value of thetas, okay. And what we understood that once we make that phase quadrature less than 1/4, we are in the regions where actually your signals variance is less than the mean value of the signal, and that is sub-Poissonian. So once we can go below that 1/4 of the variance of the phase quadrature, we'll be able to see, or we'll be able to say that whatever signal we had was a sub-Poissonian in nature.
So hello, Professor Majumdar. Yeah, just a gentle reminder about the time, and can you kindly tell when you want to stop for today, and that's that we may begin the discussions.
This is over because that is the last slide, and so yeah.
Oh, sure. Thank you so much. Yeah. Sure. So then kindly let me know when you're done, so that we can start with the discussions.
Let me conclude this one.
Sure. Thank you so much. Yeah. Thank you so much, Professor Majumdar. Yeah.
So what we have discussed so far, we have discussed that we started with squeeze light, okay, how the squeeze light can be generated. Then we have seen that how the amplitude and phase of the light can be spaced, okay, theoretically. Then we saw that there is some special quantity, okay, which is very significant, okay, in some of the cases where quantum features are very important. This is called short noise. and that is very intrinsic in the light. Okay, and if you want to do experiment of quantized light, so you have to bother with the short noise. And here we would like to squeeze the short noise. The way we can squeeze the short noise, we can choose that your signal which is sub-Persian. If you choose the signal which is sub-Persian, automatically your short noise will be squeezed. Okay, and this is the technique which I showed that here, that how this sub-Persian structure of the light can be understood. That is actually to say that the short noise is squeezed. I think if you have understood some flavor of this, okay, whatever you discuss, that will be good for whatever we are discussing. Thank you. I think let us go for the. Sorry, I just took extra 5 minutes for this. So let us go for
no problem. No problem. Yeah. Thank you so much. I mean, I'm sure this was a nice point to stop the discussion today. So I think we should just now take a few questions from the chat.
Right.
The first question we had was from Mr. Asid Barik. What is short noise limited?
So that was answered earlier, isn't it?
Yeah, thank you. Yeah, okay. Yeah. So that was at 10:43. Thank you. Yeah. Then we have one more question from Mr. Rajkumar. What is vacuum squeezing? Because the state has 0 photons, so electric field and phase in that state is 0.
Yeah. So vacuum squeezing, as you understood when we are talking about, okay, that you have a 0 photon. But when we just get 0 photon, doesn't mean that the fluctuations, that number fluctuation, that delta n, okay, which you can understand as the variance also delta n square, that is 0. So that, as I said, that if you have remembered that in last 3 classes, vacuum fluctuation is nothing but you will get 1 photon energy plus or minus. Okay, if you just go back and see. So even in the vacuum, you get a fluctuation and whose energy is 1 photon. Okay, so that you will get 1 photon extra or 1 photon lower, and that is the quantity which you get there when you are trying to understand when the quantization of the electromagnetic field in terms of simple harmonic oscillator. You got the half h cos omega. So that half h cos omega, if you add up, or if you are just below the vacuum energy level, okay, so you will get total h cos omega, that is the 1 photon energy, and that is what we are to squeeze it. Okay, when you talk about that, the squeezing of the vacuum means that we are squeezing the fluctuation of that. I think is it answers to your questions?
So, Mr. Rajkumar, I think I hope your question has been answered. So, does anyone else have any questions? So, we only have 2 chat messages, and there are also no questions in the YouTube. So, any other questions, please, fellows? Yeah. So, if there are any questions, kindly do ask them. We'll just wait for 1 or 2 minutes.
Right.
Yeah, sure. You might type it here, or you may also type it in YouTube. I'm also checking the YouTube one. There are only 3 viewers there, so not many questions over there.
Oh, fine. Okay, then maybe they'll check it later. Okay. So
yeah, absolutely. Yeah. So I think we can restrict ourselves to Zoom. Yeah.
So if you have any further questions, or if you get question later on, please actually share, and we'll try to answer in the tutorial section.
Yeah. In fact, Professor Machundar, I had one quick question, in the previous slide, where
Right.
you had to ignore, the first term, the A dagger 8 term.
Right.
So you said that could be done conveniently because it was smaller. What makes it smaller? Just to
that is relatively smaller compared to the local oscillator term. As I said,
Yeah.
that local oscillator is very strong. Okay. So if you see that detection, okay, so
Yeah.
you see that. And what we are doing at the end, we are dividing with the local oscillator intensity. Okay. So ultimately, that will be further making this your output smaller. Okay.
Absolutely. Yeah. I get it. Yeah. Sure. Thank you, Professor Majumdar. Yeah. So any other questions, please, folks?
So in that, yeah, if it is no question, so tomorrow we'll have a discussion on photon statistics. Okay.
Yeah.
So you
So,
might.
so thank you so much, Professor Majumdar, for your valuable time yet again. I mean, this has been very lively, and I must really appreciate your energy, day in and day out, coming every day proper on time, and then giving us this great lecture series. And I'm sure the participants will also have more questions. I hope they're noting it down, and then they shall be asking some of these in the tutorial sessions as well. Yeah. So on that note, I would.
They're sending mails for me.
Absolutely, Mr. Majumdar. Yeah. In fact, an email is also a very nice way to ask lengthy questions. If in case you feel shy or you feel that you need more time to formulate your questions, so kindly also do avail that option. I think on that note, it would be a great pleasure to thank Professor Majumdar yet again for yet another great lecture, and we look forward to your exposition on photon statistics tomorrow. And I also thank the participants, who have been very kind and as well as enthusiastically participating in this lecture series. And due thanks also to Dr. Sunil and Dr. Arijit for having run into the broad organization, and also to Professor P.C. Deshmukh for mentoring us overall. Yeah. So thanks to Professor Majumdar. Is there anything else you might want to add about today's session, sir?
Thank you. Okay. So let's stop sharing and.
Yeah, my pleasure. Sure, thank you so much. Yeah. So participants, if there are no more questions, do I have your permission to end the session then, Professor Majumdar? Yeah, is it fine?
Please.
Sure. So thanks a lot, colleagues, and my heartfelt thanks to Professor Majumdar once again. And on that note, I think we should just end this session.
Oh, thank you.
Thank you so much. Okay, sure. Have a great day. Yeah. See you tomorrow.